Hello, in this video we're going to find the approximate mean and variance of a function of the sample mean. Okay, so the first two pages will be a little bit thick in theory, and we're going to make use of a Taylor expansion about the function of the sample mean, and then pages 3 and 4 give a very detailed example of what we just discussed on pages 1 and 2. So if you can fast forward to pages 3 and 4, or stick with me until we get to pages 3 and 4, because then it'll make what we do on pages 1 and 2 crystal clear. So let's let x1 through xn be a sample from a population. Let's let h be a real valued function of x, our sample mean. Let's assume that the absolute value of the fourth derivative is bounded, and this is for all x. And let's assume that the fourth central moment is also finite. Then a series expansion of our function of h bar, or x bar, h of x bar, about the mean mu, and the mean is, the mean of these x's, is this. So it's x bar, is equal to h of x plus the first derivative times this, 1/2, second derivative times this, plus more junk this way. Now, let's calculate the expected value of this this term. So, and actually, that's what we want. We want the mean of this function. So that's why we're taking the expected value to obtain the mean. And so the mean of this that's a constant. So then this is a constant, so it goes into that. These are constants, so expected value of this, and the expected value of the remainder. Now this comes down. This piece, the expected value of x bar minus mu, is 0, so that goes away. This expected value is just this, and then of course we have the remainder. That's called Rn. Now here the x bar comes down, and this is the expected value, or the second central moment of x bar is sigma squared over n. Now, and I have a video where I do the second, the third, the fourth central moments of x bar to show you how we get the formulas that we're going to use in this, and I'll put a link in the description. And so this is it. So if we take the remainder off, the remainder, tends to 0 at a rate of 1 over n squared. So we use this right here as approximation to the mean of x bar. And I give a cool example on page 3 where we look at a Bernoulli random variable. So now we want to start developing the variance of h of x bar. Okay. So let's first of all take the difference of these two functions. And it's literally, you take all the terms here and subtract all the terms here, which is what we get here. Okay, right? So, the h of mu's cancel, and then all these other terms are here, and then we get this term and this term here. Now let's take the expected value of this, and we don't, of course the answer is 0, but let's look at it. So if we cover up this term, we take the expected value of the whole thing. So the expected value is the expected value of this minus, and this is a constant, so the expected value is just itself. So they have the expected value of h of x bar minus the expected value of h of x bar, so it's 0, right? So that's not a big surprise. And you can even look at the terms here. This, if you take the expected value of n, this goes to 0. And this term, since it's the expected value of, it's the second central moment of the mean, which is sigma squared over n, which is exactly this term, so those cancel. And then the expected value of this term is that term, so they cancel. So it is 0. Now let's look at the squared of this term. So what I want to show you in the next, I have to turn the page, is we want to take the square root of this, these terms. So you take this times itself, this times itself, this times itself, these of course times itself, and then you take each of these times itself, and then, you know, and then, yeah, it's actually 2 times that. So that's what we're doing on the next page. So the first 3 are the terms, you know, times themselves. So we square each of those. And then this is the cross product of, you know, the terms. And then it's this, you know, and so this is the squared. And I'll let you go through the mental math there. Now, we're going to use this term in the variance. And so there's some remainder associated with it. We want to, now we're going to try to find the variance of our function of x bar, okay? So one of the properties of the variance is if we add or subtract a constant to our function that we're trying to find the variance for, it doesn't change it. And so the variance of this is the same as this, okay? But the variance of this is the expected value of this squared minus the expected value of this, you know, quantity squared. But the expected value of this on the previous page was 0. So really, so the variance of this is just the expected value of this squared. And that's what we have here. So now let's look at the expected value. It goes into each of these. That's constant, goes to there, goes to here, goes to there, and then whatever that is. So that's what we do here. We take the expected value, that's constant, goes in, and goes in here. Now I have a video on showing how to derive, you know, what is this, what is that, you know, well, that's 0, and this is the third central moment. And so each of those goes to its respective, that's a constant. So that goes here, you know, goes here. Yep. So this ends up being sigma squared over n, but sigma squared times sigma squared is sigma to the 4th. And then we have the remainder. So then what we do here is collect like terms. Now the next step is a little bit tricky. I guess I'll show it, and because I think I'll need it in explaining it. So this term goes here. Then let's look at this term. So that term comes here. Now these terms here have sigma to the 4th, the second derivative of h squared, you know, evaluated at mu, each of those. But then they have some constant here. And yeah, here. So what we do, so this is an n squared, this is an n squared. So here, like this is n minus 1. So we can take this times the 1 and then that times the n and separate the 1 over 1/4 n cubed by itself. So since it's divided by n cubed, let's actually, we're going to stick it in the remainder. And then we're left with 3 over 4n squared. So we have 3/4 and 1/4, which is 1. And then we subtract a half, so we get a half. And so that's how these 3 terms combine to this, is we take that third, the 1 that's divided by 3. So every term in here tends to 0 at least at a rate of 1 over n cubed. Okay, so now let's look at the example using, oh, and so this is it. So this is the variance, these 3 terms. You know, and the remainder will leave off since it's an approximation. So here, so the sample is we have let x be a Bernoulli, and the mean is p, the variance is pq, you know, or 1 minus p. Let's let n be the sample size. X bar, expected value x bar is p, variance of x bar is pq over n. Let's let the function be x times 1 minus x. The first derivative is 1 minus 2x, the second derivative is minus 2. One note here, what's the third derivative? Well, the third derivative would be 0. And later in this example, I'm going to point out why that's significant. So let's find the mean and the variance of h of x bar. And the beauty of this example is we can find the exact mean and the variance of this. And that's what we do first, and then we find the approximation. So the mean of h of x bar is this. and then take the distributed in, we get the mean of x bar minus the mean of x bar squared. And there's a formula for this that says it's the variance plus x bar quantity squared, and we know all of those. So we can plug them in, and then it simplifies to this. I factor out a p here, and then I factor out a 1 minus p, and we get this. There's a note here that let me say it on the next one. Okay, so now let's look at the variance of x bar, or h of x bar. So that says we want the expected value of h of x bar squared minus the expected value of h quantity squared. So this right here squared it's actually, so we have to take this and then square it and then plug in x bar. That's what this says, and that's what this is. And then expected value of h of x bar squared is, well, the terms that we just derived here, we'd square each, and so this is it. Now let's evaluate this to find the exact variance. And this is a little bit ugly, so I created another video that evaluates the expected value of x bar squared, the expected value of x bar cubed, the expected value of x bar to the fourth. I call it the first 4 moments of the sample mean when x is a Bernoulli. And I'll again put a link to that in the description. So this is this piece, and then it's minus 2 times the expected value of x bar cubed, which is this. And then we have x bar to the fourth, expected value x bar to the fourth is this. And then we have minus this. Then I simplified it and then used maxima to find something that was, I simplified it and factored it in maxima to find this piece right here. So this is the exact variance of h of x bar. Now let's look at the approximation. So the approximation that we found on page 1 was this. That's the Taylor expansion. And then we had some remainder, but we're leaving off now. And then h of mu means plug in the mean, which we said was p, so it's p1 minus p. The second derivative was minus 2, so that's this. The variance is pq, or p1 minus p. And then this simplifies to this. And here's the note. This right here, it's 100% match to the exact mean. And the reason is, when we took the Taylor expansion of this, we stopped right here and cut it off. But this piece right here involves the third derivative of our function, and the fourth and the fifth, but those are all 0. So actually, when we cut it off here, as an approximation, since these are all 0, then the approximation is exact. So that's why this is a 100% match. Now the variance isn't the same. So if we look at the variance of h of x bar, then the formula that we came up with on page 2 is this. So now let's just start plugging in information. So 1 over n, this is 1 minus 2x, but we plug in mu, which is p, square it. That's sigma squared, which is pq, and then plus, and minus 2, the sigma to the fourth, you square the variance, and then you plug in each of these. The central moment, the third central moment, is p times 1 minus p times 1 minus 2p. And actually I have a video that shows that too, which I'll put in the description. Now we start simplifying. And actually this expression here is the best I could get it to simplify was this. And again, I used maxima. I used my own algebra and then ended up going, there's got to be a better way. And I used maxima and found this. Now you might ask, okay, so that's the theoretical results. How does it do in practice? So if we, in this example, if we say n is 10 and P is 0.3. The exact mean and variance are these, okay? The approximate mean and variance, of course the mean is going to be the same, but the variance is only off by 1, 2, 3, 4, 5, 10 thousandths, or 5 10,000ths of a, yeah, that's it. So it's really close. So anyway, this is a good mean and variance approximation. Well, that's all I have. I'm running out of time. Hopefully you enjoyed it. I sure did. And please like it and subscribe so you don't miss the next one. Thanks. Bye.